We have about 2 weeks left of classes, and then we have exam 4, and then final exams start. Just as a reminder, you are allowed to take your final exam with my other class, which one of them's Monday and one of them's Tuesday. So, it's just 1 day difference. But you have to let me know ahead of time so I know how many copies of the exam to make. So I will try and remind you of that again next week. I always forget to remind people to do the course evaluations. Those are going to be coming up soon. So please do course evaluations. What tends to happen is the people who feel very strongly in one direction or the other respond, and the people who are kind of in the middle don't really say anything, and that kind of skews what the answers are. So it's better to have a lot of data. You never have too much data. So even if you're just kind of, it was a class, that's helpful information to have in the course evaluation. So make sure you do that for all of your courses. I was also asked to make the announcement that if you haven't registered for your classes for the fall, please do so. Apparently, we got one more person. Apparently, especially upperclassmen, sophomores and juniors have not been registering. So that's good for the freshmen. It means you're getting into classes you want. All right. So that's kind of general stuff. So 2 weeks left. We have 2 chapters. Plus we need to finish up chapter 12. So planning on finishing 12 today. Had no problem with that in the last class. But I did print out the slides so that you don't have to be rushing to write everything down. And that way, the fact that I'm going a little bit faster hopefully isn't too problematic. We are starting chapter 13, which is equilibrium. Next week, if you are in lab, the lab is on Le Chatelier's principle, which is section 13.3. So what I'd like you to do over the weekend is to take a look at the first few sections. As a general rule, you want to look for, have I seen this before? Does anything look familiar? What are some of the vocabulary terms? I will post the vocabulary for 13. I haven't done that yet. And I'll have a prepare to learn for you to do. So be looking at those over the weekend. But when it comes to your lab, make sure before you go to lab, you read that 13.3 in some detail, because that's what your lab is about, is Le Chatelier's principle. So that's kind of where we're going. Hopefully we will wrap up chapter 13 before Friday, dive into acids and bases. And then the last week of classes, I think on the Monday, we have exam 4, which will cover 13 and 14. And probably have a quiz in there somewhere too. And I think that kind of covers everything I got to announce. Any questions? Okay. The reaction diagrams are the things that look like hills. We've talked about those a little bit before. You are going to want to be able to look at a diagram and identify the different parts, and we'll go through some examples of those. In particular, you want to know where the reactants and products are. You want to be able to identify EA, which is activation energy, delta H, which is how much energy change there is, and then some new terms, transition states and intermediates. And we'll talk about those in several ways today. You are also going to determine from looking at the diagram the number of steps to the reaction and which of those steps is the rate determining step. We are also going to look at proposed mechanisms. So a mechanism is just kind of line by line, what are the actual interactions of the molecules? And so from the proposed mechanism, we want to be able to identify which of the steps, again, is rate determining, and where the intermediates are. So notice these are showing up in several places, and any catalysts that might appear in the mechanism. We don't usually put catalysts on the reaction diagram, but we might show a reaction diagram that involves a catalyst. So you'll see what that means when we get to it. the proposed mechanism is going to be made up of elementary steps. And so from the elementary step, you should be able to determine the rate law. So we've already talked about rate laws. They always involve the letter K. So now we'll be able to write them from an elementary step. Anybody still need time on this one? Okay. So we've seen these reaction diagrams before. They basically look like a hill. Remember that the y-axis is going to be how much energy there is. So in here it's labeled potential energy. Sometimes it will be labeled enthalpy or H. Sometimes it will be labeled G for Gibbs free energy, but it's always energy of some kind. What that kind of energy only matters in the sense of properly calling it H or G or whatever. So you just look at the axis. The or the x-axis is the reaction progress. So this is basically like time. So you start with the reactants, go to the products. We read from left to right. That's all that is. Okay, you can determine the activation energy. In this one, we don't have any numbers, so we couldn't numerically determine it. But the activation energy is going to be the energy difference between our reactants and the top of the hill. So the top of the hill is what we have to get over in order to go to, the products. So in this reaction, we are going to have to put in a certain amount of energy to get to the products here because it's endothermic. But we can't just put in this small amount of energy. We have to actually almost double that in this case because the activation energy is so high. Okay, so think about if you have a match. Matches burn very easily, but you have a box of matches or a book of matches that isn't burning right now. And the reason is it's not going to start the reaction until you put in enough energy. So we might put in that energy by holding a flame to it. We might put in that energy by striking the match against something. If you're used to using the little clicker things, like there's a little electric spark, you can see that's the activation energy that starts the butane burning there. So you have to put in a certain amount of starting energy to get it going. And then the difference between the reactants and the products is the change in energy. Usually we will talk about the change in enthalpy, delta H. So in this case, we can see that the products are higher energy than the reactants. And because of that, that means that whatever numbers there are, the products have a higher number than the reactants. Delta means final minus initial, so we're going to get a positive number. The positive delta H tells us we have what? Endothermic or exothermic? Think of like positive Q would be the same way. Positive means endothermic. That's a good one to refresh for yourself. So delta H or Q or delta G, any of those being positive, we would call an endothermic reaction. If this hill ended down here, down below the graph, then we would call that an exothermic reaction. So you don't actually have to have the numbers to tell whether it's endothermic or exothermic. I would call this an uphill reaction because after you climb the hill, even getting down past the top of the hill, you're still higher up than you were before. So that's an endothermic reaction. All right. Oops, let me back up just a second. At the top of this, we have something we haven't seen before, and that's a molecular structure here. This structure is showing the transition state. And so what I want to point out here is that on the sides, we have between the oxygen and the nitrogen, two solid lines. Those are covalent bonds where they are sharing. But between the two chlorines and between the chlorine and the nitrogen, we have dotted lines. Those are not quite formed bonds. So they may be starting to form or they may be starting to break, but they're not being shared the way that a covalent bond is shared. So I always say covalent bonds are very, very strong. Those dotted lines indicate it is much, much weaker and it is on the way to either being torn apart or forming back together again. Okay, so that is what we call a transition state. And you can see at the bottom, the picture here also has a molecule that has solid lines, which are covalent bonds, and then the dashed lines, which are bonds that are either being formed or being broken. So for a transition state, when the molecules collide, new bonds are starting to form, as shown by the dashed lines. Old bonds are starting to weaken, also shown by the dashed lines. And we have a very weak particle, or moiety is a term we sometimes use. It's not a complete chemical. It's very, very unstable, and it's very, very short-lived. So short-lived that in most cases, we can't even measure the existence of them. So it's kind of theoretical. We figure it kind of has to happen this way, but we can't like take a snapshot picture and be like, there it is. That's what it looks like, because they're so short-lived. All right, so the next slide in the middle, dead center of the picture, is that same transition state. So we can see what is being formed and what is being broken by looking at the extremes. So on the far right-hand side, we have our reactants. And if we look at the reaction diagram at the bottom, we have what those chemicals are. So we have methylbromine and we have hydroxide. Those two particles are coming towards each other, but they are completely separate when we're at the starting point. When we're at the top of the hill, very, very near the top and at the top, that's where we start seeing these dashed lines, where we're starting to form the connection between the carbon and the oxygen. We're starting to break the bond between the bromine and the carbon. Okay. So when we are at the transition state, we can yes, hope. Polyatomic ions would be shown by solid lines because they do stay together. So even though it is an ion, it is still a covalent bond. Hope was asking about polyatomic ions. So hydroxide is an example. That's a covalent bond, strong interaction. Okay. If I'm at the top of the hill here, this particle could go either way. Just like if I put a ball right at the top of an actual hill, it could roll down backwards or it could go forwards. Okay, so I could start forming a new bond and then be like, no, I'm just going to go back to the bromine. I'm good with that. Or I could be like, nope, bromine's done. I'm into hydroxide now. Either way. So it is unstable in the sense that it's not going to stay like that, but it's also unstable in that it could go in either direction. Because of that, we think of a lot of these kinds of reactions as reversible, which means that I could theoretically start with this, the methanol and a bromide, and then move backwards to form the methylbromine and hydroxide. Okay, so that is a reversible reaction that could go in either direction. If I were going to draw this on paper, like for organic chemistry, many of you will be taking organic chemistry, we would generally use what is above the particle pictures. So the line drawings is how we would show it. Notice how it's using the wedges and the dashed lines to show the geometry. So when we talk about Lewis dot structures, I said Lewis dot structures don't show us the shape, but if I want to give some idea of the shape, I can start using these wedges. So in the reactant, I've got this hydrogen has the solid wedge with a wider part towards the hydrogen. That's indicating to me that that hydrogen is sticking out of the page coming towards me. The dashed line with the smaller part towards the hydrogen means that that one's farther away from me. So it's going backwards into the page. So you can use those wedges to kind of indicate where the geometry is. All right, so, oops. If we look at a generic diagram, this would be a good one to have on a quiz, and there's lots of questions I could ask about it. But I indicated on the first slide, some of the things I might ask you are, which of these letters indicates the transition state? So look at the letters in red. So O and H are part of the transition state, but there's an O and the H next to the letter F. There's an O and an H next to the D. There's an H2O next to the E. So which of those red letters is the transition state? Remember, a transition state is going to have weak bonds that are starting to form and starting to break. How do we indicate those? The dotted line. That's what you're going to say, right? Yeah, the dotted line. Okay, and Hope jumped in with D. D is correct. So this is the transition state. Always going to be at the top of the hill. Okay. We are going to start in a minute talking about intermediates. They're going to sound similar. Transition states are at the top of the hill. Intermediates are not. We'll be able to find them later. This diagram doesn't have it. Okay, which of these letters indicates the activation energy of the forward reaction? A. Okay, so remember that was going from the reactants to the top of the hill, right? Normally, we would put that as an arrow right underneath the hill to indicate that. There's just a lot going on in this diagram. So the same measurement can be made over here to the side. It's still going from the reactants to the top of the hill, giving us that energy. What is the enthalpy of the reaction, delta H? B, right. So that is going from the reactants to the products. Okay, so delta H is just looking at the beginning and the end. Remember when we had state functions, we said the path that we take doesn't matter. It just matters where we start and we end. So the delta H is like that. Path doesn't matter, just where we start and we end. So I don't care if I have a little hill or a great big hill, delta H isn't going to change. Okay, and then we can have a reverse activation energy. What is the value, the number value of the reverse activation energy? Reverse activation energy is going to go from the products to the top of the hill. So that is going to be C or 6. So in this case, the reverse is really, really little and the forward is very fast. So you imagine if both of these reactions are going on at the same time, it's going to be a lot easier for the reverse to happen than it is for the forward to happen because it's just got that tiny, tiny little hill. All right, so the next slide basically shows that we can have lots of different kinds of reaction diagrams. So some of them can be endothermic, some of them can be exothermic. Which of these are exothermic? Both B and C, because both of those are overall downhill. The products are lower energy than the reactants are. Okay. We can have very small activation energy like in C, or we can have very high activation energy like we have in A. Now, since this is a kinetics chapter, we're talking about how fast things are going. If we have a small activation energy, the rate is going to be really fast because there's not much of a barrier to getting that started. If I have a large activation energy like I do in A, that's going to be a slower process. I'm going to talk in a second about what can slow down or create a high activation energy. Okay, these are all showing one-step mechanisms, and in just a second we are going to show multiple step mechanisms. But let's talk about activation energy a little bit here. So activation energy is going to be based on having enough energy when two molecules collide to break bonds and form new bonds. So remember, you have to put in energy in order to pull apart the bonds, right? And you're going to release some energy as you form the new bonds, but you have to pull apart the bonds to begin with. You also have to have enough collisions that some of the collisions are facing in the right direction. I'm going to turn off the overhead here so you can see the top of this a little bit. We have ozone, O3, reacting with nitrogen monoxide. Now, in order to create our products, we need the nitrogen to run into the ozone. If I have the oxygen run into it, then I'm not going to get the bond between the nitrogen and the oxygen. So I have both, it has to face the right way, and they have to be hitting hard enough to break that bond between the oxygen, the two oxygen atoms in the ozone, okay? So at the bottom, it's showing collisions that are not strong enough to cause any damage to the ozone, not break apart the ozone. They collide and they come apart, nothing happens. So this is a little bit like you borrow your parents' car, they're like, be careful with it, I don't want to see any dents, and you're pulling out of the parking lot and you accidentally hear a little bump as you run into like a fence post or like a wall or something. Oh crap, jump out of the car and you run to the back and you're looking and there's no dent. Okay, so you heard something, there was definitely a collision, but there's no evidence of it, so you don't have to tell your parents. That's what's going on down here in the bottom. There's no reaction. You didn't hit it hard enough. But if you hit it hard enough, then you're going to have the collision and you're going to break the old bonds. Okay. All of that energy is coming from the speed of the molecules. It is the kinetic energy of the molecules running into each other. How do we speed up molecules? Temperature. We raise the temperature. And so this is why temperature has an effect on our rates, because it's going to increase the speed of the collisions. It's also going to increase the number of collisions, but it's going to increase the speed. And so more of the molecules are going to have enough energy to break bonds. All right, reaction mechanisms. So as I mentioned before, a mechanism is going to say, well, overall, I know I put A and B in my beaker, and at the end of the day, I had E and F. So I had a reaction. But what were the actual steps that took place? Which molecules actually combined with one another? Okay, so we want to know, how do the molecules interact to give the final products, which means what are those steps? And we want to know about active sites. Now, in this class, we don't really deal with active sites, but the idea of active sites was on that last slide, that we had to have the nitrogen interaction with the oxygen. If you take organic chemistry, many of you will take organic next year, you're going to deal a lot with that. You're going to actually draw out the molecules and say, this part of this molecule is going to interact with this part of this molecule. And usually it's going to be an attraction between something that's a little bit positive Sorry about that. The stuff in red is the reactants, the stuff in blue is the products, and the things that get crossed out are the things we call intermediates. So C and D in this are what we consider to be intermediates. All right. Come on. Okay, so when we have a mechanism that has more than one step, we can see this on a reaction diagram because we're going to have more than one hill. So on the right is what we, or sorry, the left is what we've looked at before, a one-step mechanism. This is a two-step mechanism. And we can tell it's two steps because it has two hills. So if we want to determine how many steps a reaction mechanism has, we just count the number of hills. So I'm going to zoom in on the two-step reaction mechanism. We see there are two hills. There are also two transition states. So at the tops of the hills, we will see transition states. We don't usually draw out the molecules. It is drawn out here. Sometimes we will indicate it with a star or an asterisk. And just remember that that is really short-lived. So what about the intermediates? They're kind of short-lived because they appear and then they disappear, right? They are going to be in the valleys between the steps. So we see here the fluoride or the fluorine atom here, just like the chlorine atom I said before, that's a free radical. It exists for a short amount of time and then it disappears. Okay. The NO2 is just a second reactant that's in there, but the fluorine atom. Each step can have its own activation energy. So you can see that the first step is really big. That's indicated to the left-hand side. The second step, that activation energy is really, really small. Okay, so you can see that over here on the right-hand side. Probably there is plenty of energy from getting over that first hill to just automatically go over the second hill. Kind of like in a roller coaster, you start at the top and you have enough momentum from going over your first big hill to going over the next hills. So usually we can just kind of tumble right through to the end of the reaction that way. All right, and then we can also see on this reaction diagram, we can measure the delta H, which is shown at the bottom, and we can imagine where reverse activation energies and things would be. Yes?
So the little valley is the intermediate?
The little valley is where we find the intermediates. In this, they are showing that I'm going to have NO2F as a product here. That's one of my final products, but I only formed one of them. This is another reactant. So there were two of them. One of them is appearing here. So F is the intermediate because it's not part of the overall. So if we want to locate the intermediates on a multi-step reaction diagram, we locate them in the valleys between the steps. Okay, catalysts. Catalysts in some ways look like intermediates because they do not appear in the overall reaction. So if we were lining everything up, we would cross them out just like we did C and D before. What is the purpose of a catalyst? It what? It lowers the activation energy. And why would we want to lower the activation energy? What happens to the rate when we lower it? It speeds up the reaction. Okay, so we're speeding up the activation energy by lowering the we are speeding up the reaction by lowering the activation energy. So I could have a reaction where I need A and B to get together to form C. So this is very typical of something that might happen in your body. You have two different molecules that need to get together in order for something to happen in your body. But the chances of them running into each other in just the right way so that the reaction occurs is pretty small. And so if I just let it happen on its own, it might take months or years. But instead, you have enzymes. So enzymes are protein catalysts. So they're catalysts in every term. They speed up the reaction. They're not in the overall picture. But what it's going to do, think of X as your enzyme. The enzyme's going to grab onto A and hold it in place so that the part that needs to react with B is sticking out. And then it waits for C to come along. C collides in just the right way. So first, reacts with A. So the two things together are Y. Then Y is the two things holding on to each other, reacts with B. And then once C is formed, whooped, went too fast. Once C is formed, then the enzyme lets go, got your new molecule, and the enzyme X is back the way it was before. Okay, that's your basic idea of how an enzyme works. I'm sure Dr. Hughes will tell you it's far more complicated than that, and there's a lot of different ways that you can have it happen, but that's our basic story. Okay, so what does this look like on a reaction diagram? This means that since we have a different activation energy, we have a different line. So the green line is showing us A and B taking their time to run into each other to form our products. The purple line is 2 steps. So it increased our number of steps, but it's lower in energy, which means I don't have to have the molecules running into each other quite so fast. I don't have to have a really high temperature for that to happen. I just have to have my enzyme or my catalyst grab onto A, hold it in place so B can come along and collide, and then they let go. So the activation energy is lower. What about delta H? Is delta H different between the two of them? No, the overall start to finish is still the same, right? That was the idea of our state functions, is that only thing that matters is the beginning and the end. It doesn't matter how high the hill is. So whether I did it all on my own or I used a little catalyst to cheat, the overall change was the same. But the catalyst lowered the activation energy. All right. Sometimes you will hear the term heterogeneous catalyst. This just means that it's in a different phase. So the stuff happening in your body, that's basically all in aqueous solution, right? They're all in the same place. They're all in your blood or in your cells or wherever these things are going on. In a car, you might have a catalytic converter. So your car can't be made of gas. It's usually made of solids. And so part of the catalytic converter might be metal like platinum. And the platinum acts kind of like the glue on a Post-it note, where it's just a little bit sticky, but not very sticky. So as we have molecules come along, they sort of stick a little bit to your catalytic converter, which holds them in place long enough to react with one another. And so this is just showing an example if you were trying to get ethane to react with hydrogen. In your car, you might have a big nasty molecule that could be cancerous. The converter holds onto it long enough to break it up into less harmful species. Big picture here is heterogeneous means it's not in the same phase. It's probably a solid, whereas the reactants are not. Okay, how do we determine rate laws? Because remember, this is the chapter on rates. How do we determine rate laws from the mechanism? So the mechanism is showing us elementary steps, and the elementary steps show the actual collision. So if I say this top thing is an elementary step, I'm saying that not just that ozone and nitrogen monoxide are in the same beaker and then something happens that I can't see. I'm saying actually ozone reacts actually with nitrogen monoxide. Those two things have to collide. That one of the steps is for a collision between those two things. So because of that, the rate of the elementary step can be shown by those concentrations. Okay, so if my reaction here is what's actually happening in the beaker, it's not just that they're wandering around together and I don't know how they collide, but I know those two things collide, then I can say, if I increase ozone, I'm going to increase those collisions. If I increase nitrogen monoxide, I'm going to increase those collisions. That is why there is a dependence on those. But if this mechanism here, this is just one part of a mechanism, if another reactant in there is, say, water, and the water's not part of this step, then whether I have a lot of water or a little water is not going to impact how fast that step occurs, because it's not part of that step, okay? So we can write the rate law, which remember the rate law always has K in it, by saying it is K times each of those reactants, and then we use for our exponents the coefficients. So I know I spent the first half of this chapter saying you can't look at the equation, the coefficients don't tell you anything. That's because we were looking at overall reactions. If I know it is an elementary step, and only if I know it's an elementary step, I can use the coefficients. We'll look at some more examples of that in just a second. All right. The first bullet point, same as the last bullet point on the other thing. I just cut and pasted. The chart here is just showing you some terminology. I'm not going to have you memorize this or ask you about it, but you may see this in your reading. So this is just how we describe how many reactants we have. If it is unimolecular, there is only one reactant. If it is bimolecular, I have two molecules. They might be two different molecules, or it might be one molecule that I have one chemical that I have two molecules of. So I could have two of A or I could have A of B. And if it is termolecular, then I have three molecules present. I don't talk about anything over termolecular because remember, this is showing the actual collisions. So for two things to run into each other, yeah, that happens, right? Have you ever had a collision where you run into two other people at exactly the same time? Probably not, or if you have, it's probably not been very often, right? We don't typically have three things all collide all at the same time, okay? And so an elementary step that is termolecular is really unusual. And this is why way back at the beginning we said, well, we don't really have third order or fourth order or fifth order reactions, because that would mean I actually have 5 things colliding with each other at the same time. And the odds of 5 things running into each other and all of them facing the right way and all of them having enough energy for the reaction to happen, that's just astronomically low. That's just not going to happen. So basically most reactions happen at a bimolecular level. 2 things run into each other. Okay. So our rate determining step, I said you should be able to look at a mechanism and determine the rate determining step. You have to be given additional information. So far I just told you these are what the steps are. The additional information you would be given is how fast each step is. So if I look at this example, got lots of letters and chemicals over there on the left-hand side, but if I want to know the rate determining step, all I'm looking at is it fast or is it slow? So you would be provided, is it fast or is it slow? And you just look for the slow one. Whatever the slowest step is, that's your rate determining step. So we would say in this case, step 2 is our rate determining step. Okay, so I said from the reaction mechanism, you need to be able to determine the rate determining step. You should be able to identify intermediates. So are there any intermediates in here? Remember, an intermediate is produced first, so it shows up on the product side first, and then shows up as a reactant, so it's not in the overall equation. And if we look at the overall equation, we can tell which things are not in there. So what might be an intermediate? What gets crossed out as we're adding all of those things together? Don't have an individual hydrogen atom, so which hydrogen? The OH, okay? So OH shows up here, it's product first, and then it shows up in step 3 as a reactant, so it gets used up, so it's not in the overall, so OH is an intermediate, okay? And your slide probably shows you, or your notes probably show you there are 2 other intermediates, right? The HClO and the HI. There's also a catalyst in here. What would serve as the catalyst? Catalyst is going to show up first as a reactant, right? Because we have to put it in order to speed up the reaction, and then it's going to get spit out at the end, but it gets crossed out when we add everything together. So what chemical is not in the overall reaction, but shows up first as a reactant? H2O, water. So this is telling us that water is helping this reaction to move along, but the water that I end up with at the end is exactly the same amount I had at the beginning. Okay. We cannot tell from this mechanism if there is a different mechanism that does not involve water. So theoretically, there could be a different mechanism, but we can't tell just by looking at one mechanism. All right. So this is more useful for people who are going on in their chemistry studies. This isn't stuff that I would necessarily ask you about, but if you are looking at a mechanism and you want to know, is this reasonable? First of all, you should be able to add up the steps and get the overall reaction. You want to check to make sure that each of the steps only has either one or two reactants in it, because like we said, it's possible for three things to collide with one another, but that'd be pretty rare, and any more than that, it's just not going to happen. And then the last part really is something that we won't deal with. The rate determining step should match the rate law. So first of all, you'd have to be told what the rate law was, and then you would have to look at the slow step and determine what the rate law was. But what we want to do is to be able to determine that rate law. Okay, so first of all, quick question. Which is our rate determining step, 1, 2, or 3? 1, because it is the slow step. That's all we need to know about that. So basically, if I gave you a mechanism like this, I would mostly ask you, what's the rate determining step? Are there any intermediates? Do you see an intermediate? What? You're nodding. OH, yeah. So it's made in 2 different steps, and then it is used up. And then I could ask you about catalysts. Okay. Determining the rate law. What we do is we take the slow step and then we say, what are the reactants? H2O2 and Br minus. Put those in brackets to show the concentration. Slap a K in front because it is a rate law, and rate laws always have K, and that's going to give us the rate law for that step. Now, if the slow step is the first step, that makes it easy. Oh yeah, also you should be able to tell how many steps the mechanism is. So this is a 3-step mechanism. Can you tell why it's a 3-step mechanism? Because there's 3 hills. Okay. You can also say the hill with the lowest activation energy is the slowest one. To me, both 1 and 2 look like they're about the same amount of activation energy in this. So it's kind of hard to tell from that one. Okay, this is the one I wanted to look at. Does this rate law match this elementary step? So remember, if it's an elementary step, we take the reactants, put those in brackets, and then the coefficients become our exponents. So that matches, right? Now, so this is a proposed mechanism. Is this a likely mechanism to have it all happen in one step? Why not? Because there's 3 molecules that would have to collide. So that's pretty unlikely. So we might say instead, it's happening in 2 steps. And this is where this can become a little bit more complicated. If you are done with chemistry after this year, you don't have to worry about this. But if you are doing like pre-med or if you're going to pharmacy school or something, you may have to do something like this on an exam. If we do the rate law for the slow step, which is our predetermining step, what would the rate law be? First of all, K, right? That's the rate law. And then what? In brackets, N2O2, and then in brackets, O2. So that's the rate law for this step. But when we want the rate law for the overall reaction, we don't want intermediates in there, okay? So if you look at the remaining slides on this, it just shows you it's just algebra. It looks like a lot of letters, but it's just algebra where you're substituting in from the reaction above. If you want me to go through with you step by step on how to do that, if that's something that you think you might have to do in the future, I'm happy to do that, but we're kind of at the end of our time.
All right. Any questions?